One of the reactions we talked about several days ago in class when we were doing our overview of enolate reactions were conjugate addition reactions. And we haven't talked a ton about them in class, and they are going to prove useful when you're doing daily problems that are due on Wednesday. So I wanted to give you an overview, preview, overview of these reactions, and I want to talk about three different types of carbon nucleophiles we can use to form carbon-carbon bonds using conjugate addition reactions. And again, conjugate addition, we're going to add a nucleophile to the beta position of a conjugated enone. Right? So let's look at different carbon nucleophiles that we can use to do these sorts of reactions. Right? So carbon nucleophiles for conjugate additions. The first one we've seen and used already. It's a Gilman reagent. Alright, so R2 copper lithium. We should be familiar with this, and it's something that we've used quite frequently in the past, so we should be ready to use that. Two, a functional group that we learned how to make, but we didn't really use very much, right? And that's an enamine. Right, remember the structure of an enamine looks like that. Right, those turn out to be excellent carbon nucleophiles for conjugate addition reactions. Right, and this was chemistry that was pioneered by Gilbert Stork. Gilbert Stork is a professor at Columbia. Right, and then the final one, and the most useful, are enolates of 1,3-dicarbonyls. Right, so again, we're talking about those sorts of enolates. Right, very, very useful carbon nucleophiles. They're great for conjugate addition reactions. And just a note here is that standard enolates, which again, standard enolate, I'm thinking about something like that that's not doubly resonance stabilized. Standard enolates are poor nucleophiles for conjugate additions. Right? Those nucleophiles often end up doing both conjugate and direct addition. You get mixtures of products. Sometimes you end up getting aldol products. So these things are the sorts of enolates that we want to use. If you want to do a reaction of something that looks like this, that's where the Stork enamine chemistry becomes really valuable. It enables you to do a reaction that looks like this in terms of the product, but you don't have the same sorts of problems. So what I want to do is just go through the mechanisms for these, and then you can think about how you might use these when you go through working on the daily problems. Right, so first, let's look at the Gilman reagent, just to review. Right, and just to practice drawing our curved arrows for a conjugate addition reaction. So there's our conjugated enone. We can react that. Again, the first step is going to be reacting it with a copper lithium. And again, remember the lithium is just along for the ride. It's a positive ion. And then the copper is negatively charged. One of the groups is going to react with the enone, and then the second step is going to be just an acid quench. Right? So we're going to do the conjugate addition, where this adds to the beta position, again, alpha, beta. The beta position is electrophilic, delta positive. You can draw out the resonance structures for that to remind yourself. Right? And we end up with a product that is an enolate. Right? And we've added the nucleophile to that beta position, right? And then the acid quench. Right, so we've taken our conjugated enone, and again, we've added a nucleophile to the beta position by a conjugate addition. Right, so again, we've done that before. Let's now talk about what happens when we do these enamine reactions and the enolates of 1,3-dicarbonyls. All right, so let's look at the storic-enamine synthesis. This is just a variation on the Michael reaction, which is essentially enolate-type compounds adding to conjugated enones. So the first thing we need to do is just remember how we make an enamine. So we can start with a ketone, right? So we'll just take acetone. We're going to react this with catalytic acid. We're going to throw in usually a cyclic secondary amine. The conditions are to remove water to drive the equilibrium. This is a great mechanism problem just to review how this stuff works. Right? So I'll let you do that on your own. Right? Once you figure out the mechanism, you end up with that enamine as the product. Right? That's going to be the nucleophile when we do the conjugate addition reaction. Right? So now we'll do the second step. So this was the first step. Right? And then the second step, we're going to add this to our conjugated enone. Right? So this is step number 2. And enamines are great nucleophiles, so that's going to react just like our enolate in terms of the nitrogen pushing electrons into that pi bond, making that carbon a good nucleophile, right? So that we end up with conjugate addition reaction. That gives us an iminium ion and an enolate. And that ends up being stable until we add in step number 3, some acid and water. That's going to protonate the enolate to give you a carbonyl. And in a mechanism that, again, I'll let you go through on your own, review of stuff we've done last semester with acid and water reacting with an iminium ion. That iminium turns back into a carbonyl, and you would end up losing the amine as it's protonated in its protonated form. Right? So the key with this storic-enamine chemistry is that you end up making a 1,5-dicarbonyl. And again, a 1,5-dicarbonyl is our retron for the Michael reaction. Right? So this is a Michael retron, right? Telling you that you can use this storic chemistry. Right? And then the final reaction is a Michael reaction with a 1,3-dicarbonyl enolate. Right? And this is probably the most common Michael reactions. These are the most common Michael reactions where you start with a 1,3-dicarbonyl, react that with your conjugated enone, and these reactions are very easily run with catalytic sodium hydroxide. And you generate, again, the 1,5-dicarbonyl product, which again is the Michael retron. Right, and if we think about the mechanism for this reaction, again, we very clearly have these acidic protons, so hydroxide can come and pull off one of those protons. Gives us the enolate, and the enolate can react with the conjugated enone. Right, that gives you an enolate product, and to get to the final product, the water that we generated in the first step can react with the enolate, regenerates the hydroxide catalyst, and then gives us the final product. Right? So again, very, very useful chemistry. We're going to see Michael reactions quite often, and hopefully this will help you when you're thinking about what you're going to do for the daily problems for Wednesday, because some of these reactions are going to prove useful in your synthesis and mechanism problems. And the final thing to say is don't forget too that we can think about using the malonic ester and the acetoacetic ester in this position for this 1,3-dicarbonyl, doing similar sorts of chemistry, and then doing a decarboxylation so that we end up, instead of with 3 carbonyls in the product, we end up with 2 in the product. So that's something to think about as you work on your problems for tomorrow.